we will discuss that the high sensitivity was a must for a sampler, which includes a low DC offset. Therefore, we must include a DC offset calibration to reduce the input offset as little as possible. In the Why DC offset cancellation video, we introduced a simple DC offset cancellation approach widely applied in ergo design for a long time. Can we apply it to our strong arm latch? If yes, think about the summing amplifier for 5 seconds. Bingo! As we know, we cannot put the sampler right after the termination to avoid the clock kicking back to the receiver front end. In addition, any CTLE or pre-amplifier before the sampler will not only help equalize the ISI, but also improve the sampler's input sensitivity. Therefore, before any sampler, the preamp or summing amplifier should be available, and the preamp is a power-efficient way of cancelling the DC offset. Think about the signal path images for 5 seconds. Right, the extra capacitance loading of the DC offset cancellation at the signal path is very little through any tiny differential pattern devices. The huge calibration deck is tunable DC current outside the signal path, and the DEX device and passive capacitance will not degrade the signal bandwidth or add extra power. But this will have another nonlinear impact on the preamp if both DC offsets of the preamp and the sampler are too much. Is that possible? Think about the gain images of the preamp for 5 seconds. Correct. The cancellation deck is at the preamp's output and the sampler's input. Unfortunately, the preamp may require a gain of 2 to 3. If the input offset is 5 millimole RMS, then the output offset from the preamp could be 15 millivolt RMS plus sampler's 10 millivolt RMS input offset. The cancellation deck could cancel the peak voltage up to 110 millivolt in 6 sigma. Then the preamp could reduce the eye opening due to the nonlinearity caused by the output asymmetric operating point greater than 100 millivolt. Remember, in the Y sine LMS adaptation for DFE, the linearity of the summing amplifier must be maintained. Otherwise, the sine LMS algorithm won't be able to find the optimal point or even fail to converge. What can we do? Think about several images for 5 seconds. Great. We just calibrate the DC offset one by one, respectively, such that the offset cancellation deck don't have so much dynamic range to degrade the linearity. But how do we calibrate the strong arm latch itself? Think about its main offset contributors for 5 seconds. Correct. As we discussed in the Why strong arm latch video, the input differential was the main contributor, which is related to the operation as follows. First, during the reset state, there is no sampling and DC offset. Second, during the rejection state, the DC offset impact is not significant because the nonlinearity operation and a big gain refer to the input. Third, in the amplification state, the voltage gain is provided by the flow of the charge from CP and CQ. Therefore, we could create a symmetric capacitance to cancel the DC offset through different discharge rate at node P and node Q. Alright, do you see any speed issue here? Think about the signal path images one more time. Bingo, and unfortunately, we accidentally put the cancellation deck inside the signal path. Obviously, to reduce the offset from a big value to a reasonable value, a greater number of small unit capacitor bank must be connected to P and Q, not only degrading the speed, but also raising the power dissipation CVF curve. Again, this approach is similar to a brute force way of fighting the offset with sizing, which is very expensive. For example, 4x in capacitance and hence power, just for 2x offset reduction. Burning the power at the DC instead of the high-speed signal is a waste. So, what can we do? Think about the preamp images of pulling the cancellation deck away from the signal path for 5 seconds. Perfect. Remember, the preamp just added a tiny differential pair at the output. In the strong-arm latch, we could add another DC path differential input and connect to the differential output P and Q as well. There is some capacitance loading, but small enough, since we could adjust the DC voltage and the gate inputs respectively to create a symmetric bias voltage to cancel the DC offset easily. The input DC adjustment was done with 2 huge R deck out of the signal path. Once the DC offset calibration of the sampler is done. What's next? Good. Assuming the sampler's residual offset is little, then we could shorten the preamp's both inputs to VDD and then do the previous current deck calibration for the preamp only. If there's any CTLE stage before the preamp or summing amplifier, what should you do? Correct. Just keep the same procedures for each previous CTLE stage until it's done. But this is still not perfect. Think about the variation images for 5 seconds. Bingo! The limitation of this kind of offline DC offset cancellation cannot adjust when there's a voltage or temperature shift. So we must tolerate the increasing residual offset due to the supply voltage or temperature variation, and just put those impairments into the link budget. If we don't tolerate the residual offset, we must add a background calibration in the closed loop as we mentioned in the white DC offset cancellation video. Here are a summarized image of why we need a dedicated DC offset cancellation for strong arm latch, pre-amplifier, summer, and CTLE. Since we must add a preamp or CTLE before the sampler to improve the input sensitivity, we could just leverage the existing preamp and put a DC offset cancellation deck underneath. Even though we added a differential pair, the size is tiny without adding the power or speed overhead. But the asymmetric operating point and the preamp output degrades its linearity and could degrade the equation adaptation and hence the eye opening. Therefore, separating the DC offset calibration at each stage, sampler, preamp, CTLE, would reduce the nonlinearity. For the sampler only, the capacitor bank at the drain of the differential pair can cancel the DC offset, but it's inside the signal path to degrade the speed and add power. Fortunately, we could apply the same idea of the preamp's cancellation deck by putting a tiny differential pair to the sampler output, but asymmetrically adjusting his input DC offset voltage by a R deck outside the signal path to cancel the DC offset. As long as the sampler's DC cancellation is done, we can do the preamp, CTLE, etc. to each previous stage one by one. The only limitation of the offline DC offset cancellation is the tolerance of the supply and temperature variation. We could either add those residual offset into the link budget or add a background calibration to reduce further during the supply and temperature variations. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback. and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.